Okay, so this last little section in chapter 12, 12.6, is a little bit shorter than the previous section, and the focus here is on a specific set of surfaces, two different types of surfaces. One, something that we call cylinders, which is kind of a generalization of what you imagine a cylinder to be, and then quadric surfaces. So starting with a cylinder, the book gives this definition of a cylinder, which is a little bit hard to imagine until you've sort of seen some examples, but we define a cylinder to be the set of all lines that are parallel to a given line and passing through a given plane curve. So the example kind of shown here, this is something that we might call a parabolic cylinder. But the way I kind of like to think of a cylinder in less formal terms is if you look at the graph of some particular curve in the plane. So for example, if we focus here on the xz plane, you can see this parabola kind of in the middle. And then if you imagine taking that parabola and translating it along a line that's perpendicular to the plane containing that curve. So for example, the y-axis is perpendicular or orthogonal to the xz plane. And so if I imagine taking this parabola and sort of shifting it along the y-axis, either in the positive or negative direction, it sort of sweeps out this surface that looks kind of like, looks a little bit like a folded up piece of paper or a taco shell or something like that. But this is what we would call a parabolic cylinder. Down here in this example, I'm going to talk through this example in a second. This is the kind of surface that you would normally think of as being a cylinder. In this case, the curve that we're thinking of as translating along an axis or a line, kind of like this parabola was moved along the y-axis. The curve this time is a circle. You can see the circle lives in the xy plane here. And so there's that circle. It's making the base of that cylinder. And then if we imagine taking that circle and translating it up and down the z-axis, which is perpendicular to the xy plane, it sort of sweeps out this circular cylinder. This is something we would call a right circular cylinder. So again, the way that we're using the term cylinder in this class is more general than what people usually mean. Usually when you say cylinder, you're talking about this specific surface. For this example, notice this came from an equation. It says graph the surface x squared plus y squared equals 1. And because it's being described as a surface, we have to think of it that way. Normally you look at this equation, x squared plus y squared equals 1, and you think that's the unit circle, right? But specifically, it's the unit circle in the xy plane. So this, and that's 1, and that's 1 up there. And this is commonly how we deal with surfaces like cylinders, or we're going to see quadric surfaces. This is called a trace. I'm going to define that term a little bit later, just down in this paragraph down here. But basically, it's an intersection between a surface that we want to graph and some plane, in this case the xy plane. So the xy plane cuts through this circular cylinder and creates a cross-section that looks like the unit circle. But then what I do is I start by looking at the graph of this equation in the xy plane, because those are the variables that are being used. And then that forms kind of the base of my cylinder, and then whichever variable is not present here, so the z, which is not present here, is allowed to vary freely. And that's what causes this shift of the circle up and down the z-axis to sweep out this cylinder here. Okay, so you can think of this parabola the exact same way. Notice this parabola wasn't given an equation, but again, that cross-section appears to live in the yz plane. So this might actually be the graph of z equals y squared, because if I were to look at the graph of that equation in the yz plane, I know that it would look just like a parabola, right? And that's what we have here. And because x is not present in this equation, oh, I'm sorry, I should have said z equals x squared. I got that mixed up. Because y is not present in this equation, y is free to vary, and that's what drags the parabola along the y-axis in that way. Okay, so cylinders are fairly simple surfaces, and oftentimes in an equation, your clue that you're looking at some type of cylinder is that you'll have typically 2 out of the 3 variables present, and that third variable just won't appear anywhere. That third variable is what's giving you that cylindrical shape to that surface. The major topic for this section, though, is the quadric surfaces. So quadric surfaces are the 3-dimensional analog to the conic sections in the plane. When you talk about conic sections, typically in intermediate algebra, you're taught from the very beginning that conic sections are the result or the graphs of quadratic equations in 2 variables. So quadratic equations where both an x and a y are present there. And then you kind of go through the conic sections. Circles, which are actually special cases of ellipses, parabolas, and hyperbolas. Those are all what we call the non-degenerate conic sections. And then there's degenerate cases, which we're not going to worry about. So those are covered in algebra. If we jump up one more variable and talk about quadratic equations in 3 variables, which could potentially look as complicated as this. A through j are all constant coefficients here, and you notice you have x, y, and z variables all showing up throughout. This is a quadratic equation in 3 variables. The result, or the graph of one of these, will look like a quadric surface, and we'll look at what all the quadric surfaces are momentarily. As I mentioned with cylinders, it's usually helpful when graphing a quadric surface to think about its traces. Specifically, we examine the traces of an equation in each of the coordinate planes, and then oftentimes we also look at traces in planes that are parallel to the coordinate plane. So let's kind of make sense of this with an example. This is an example straight out of your book, and I use this example because I could use the images, which I really struggle with drawing. So I want to go through this sort of bit by bit. This equation here, z equals y squared minus x squared, results in a quadric surface, something that we're going to call a hyperbolic paraboloid, which we'll make sense of in a minute. So the idea here is to first look at what's happening in the coordinate planes. And what that means, like for example, you notice there's 3 sets of coordinate axes here. I have a y and a z axis here, an x and a z, and an x and a y. So this means that we're looking at the yz plane, xz plane, and xy plane. It's like I took them out of 3 space and laid them each flat on the page so I could just focus in 2 dimensions. Remember, for example, here in the yz plane, we're looking at where x is equal to 0, right? So if I plugged a 0 in for x here, then this simplifies down to z equals y squared, which is just this parabola right here. And you notice the 0 here. This 0 indicates what we plugged in for x, right? Now, before I talk about where these other parabolas are coming from, this first parabola here, which is the trace in the yz plane, if I were to bring this back into 3 dimensions and look at the yz plane, that parabola would be living right here. You could see that its vertex is at the origin, and I'm trying to take this 2-dimensional little trace and fit it in almost like a slice of this this overall surface in just the yz plane in 3 space. Okay, but remember, we don't always want to just look at the coordinate planes. We also want to focus on planes that are parallel to those coordinate planes. So those are going to be planes whose equations are of the form x equals k for some constant k. And that's where we plug in different values for x. So for example, if I plug in x equals either plus or minus 1, notice I'm squaring it, so I would get the same thing in either case. I would get z equals y squared minus 1 in either of those cases. That's going to look like this original parabola shifted down 1 unit. So when x is equal to either positive 1 or negative 1, which is what these values here are indicating, then we would have a parabola in that cross section that looks like this. So moving that into 3 space, that might look like these 2 parabolas right here. Okay? And then you could plug in lots of different values for k, and you're going to see that because we're subtracting that, the further away x is from 0, the further down we're going to be translating those parabolas. Now take a look at this second set of traces right here. These traces are in planes that are parallel to the xz plane. So what that means is that in the xz plane, we're looking at where y is equal to 0, or if we're talking about a plane that's parallel to the xz plane, we're talking about planes whose equations look like y equals k for some constant k. So that means we're just plugging in different constants for y and then seeing what the resulting equation is. For example, if I plug y equals 0 into this, then I get z equals negative x squared. So that would be like the parabola opening, the parabola whose vertex is at the origin, opening downward. That's this guy right here, corresponding to that 0. And then if I plug in different values for y, I get different positive constants here, which take that parabola and shift it upward for those different k's. Okay, so taking these traces and fitting them into 3 space where y equals 0, plus or minus 1, plus or minus 2, although those ones aren't shown here, I can see that these parabolas would exist, where you're seeing them here, in these kind of, again, parallel slices. And then I could do the same thing in the xz plane. So again, in the xz plane, we're looking at where z is equal to some constant. In the xz plane specifically, we're looking at where z is equal to 0. If z was equal to 0, that would imply that we have 0 equals y squared minus x squared. Or, remember, that's equivalent to y squared equals x squared. And if you take square roots of both sides, this is actually the same thing as y equals plus or minus the absolute value of x. Remember, the square root of x squared is not, I was writing that without you being able to see it. The square root of x squared is not necessarily x, it's the absolute value of x. And the plus or minus means I took square roots of both sides. That creates this sort of x shape because the positive absolute value of x creates this v shape up on top. That's what that graph looks like. The negative absolute value of x creates this upside down v. So we have, again, that kind of x shape. As soon as I start plugging in values other than 0 for z, so for example, if I plug in a 1 for z, then I have 1 equals y squared minus x squared. Okay, this is the equation of a hyperbola. And I can graph that hyperbola. It would be oriented vertically because the y squared is the positive of these two terms here. And so you get a hyperbola looking like the ones that we see here in green. And I could plug in different values here and get, a bunch of hyperbolas that would act as traces of our surface in that case. Here you see these traces that we sketched out in 2 dimensions fitted in as sort of slices in 3 space. And you kind of see how they stack up. So again, there's that X shape that I described, passes through the origin, and then these hyperbolas that open in a kind of around the y-axis, if you will. If we take all of these traces and sort of fit them together, what you end up with is this surface down here, and you kind of have to visualize for yourself how all of these fit together to create this. This is, again, something that we call a hyperbolic paraboloid, and that's because its traces all look like either hyperbolas or parabolas. This specific surface is of particular interest to us in chapter 14, where we start looking at optimization problems. Specifically because of this point here at the origin, it's something that we call a saddle point. You notice that this surface looks kind of like a saddle that you would throw on a horse. Those play a particular role in optimization problems. So we'll define saddle point more formally there and talk about their relevance in those optimization problems. Okay, a couple other surfaces that we want to look at. Now, I went through this one really thoroughly. Again, this was all pulled out of your book, and I liked being able to use the images from your book. It's a little bit more clear that way than me trying to draw them by hand. I'll just be upfront. I'm not the most skilled at sketching these three-dimensional graphs. I do what I can. So typically what happens is once you've gotten a sense of how these quadric surfaces look, you know, we've looked at one here, and we're going to look at different types as well, but once you've gotten a sense of what they look like, oftentimes you can actually kind of get away with only looking at the traces in the coordinate planes themselves. If you want a really accurate graph, you really should be plugging in other values for x, y, and z to get these other slices. But again, oftentimes it's sufficient to just look at the coordinate planes and then sort of fill in the gaps based on what we know these quadric surfaces should look like. So I'm gonna do that with this example to sort of illustrate. This guy right here, we want to graph this equation: 4x squared plus 16y squared plus z squared minus 16 equals 0. Okay, and right now, the form of this equation looks a lot like this general quadratic in 3 variables that we talked about, where we have an a, b, and a c, none of these terms, and then we have a j. So again, an x squared, a y squared, a z squared, and then a constant term. So that's kind of like where d through I, those coefficients are all 0. Rather than work with this equation in the form that I currently have it in, I'm going to add the 16 over to both sides and then divide both sides by 16. That's going to give me this: x squared over 4 plus y squared, which I can write as y squared over 1. You'll see why I'm doing that in a minute. Plus z squared over 16 equals 1. Okay? This is a preferable form for this equation to be in. And now what I'm going to do is look at the traces in just the coordinate planes themselves. Again, if I wanted to be more thorough, I could focus instead on, start with x, y. I could focus instead on not just the coordinate planes, but, you know, all of those parallel slices. So if I'm in the x, y plane, then I'm looking at the equation here where z is equal to 0. So if I plug 0 in for z, this becomes x squared over 4 plus y squared over 1 equals 1. I recognize that as the equation of an ellipse. And because this isn't an algebra class, I'm going to trust that you remember how we graph ellipses. This one is going to look like this. It's centered at the origin, and it has x-intercepts at plus or minus 2, y-intercepts at -1 and +1. Okay? Let's take a look at our yz plane next. Or no, let's do our xz plane. What would the trace in the xz plane look like? Well, again, we're taking the equation, and because y is absent here, y is what we're plugging in a 0 for. So if I plug a 0 in for y into this equation, I end up with x squared over 4 plus z squared over 16 equals 1. So again, an ellipse centered at the origin, x-intercepts at plus or minus 2, z-intercepts at plus or minus 4. 2, 3, 4. So now we have an ellipse that looks like this. Okay? Lopsided, I know. And again, that's what happens when I try to do these things freehand. Okay, I need a trace in the YZ plane now. I'm going to sneak this one down here. So YZ plane. All right, if we're in the YZ plane, then we're plugging in a 0 for x. If I did that, then this equation simplifies to y squared over 1 plus z squared over 16 equals 1. Yet another ellipse. So this ellipse is going to be centered at the origin again. Y-intercepts at plus or minus 1. Z-intercepts at plus or minus 4. 1, 2, 3, 4. And another ellipse that looks like this. Okay? So now that I have those traces, I'm going to go into 3 space now to try and create a surface out of this. Okay, X, Y, Z. Actually, I probably should label that my X. You usually want your positive axes to be where the labels show up. Starting with my XZ plane, that's these two axes right here. And X, again, my intercepts are plus or minus 2, 1, 2. And my Y intercepts are plus or minus 1, like that. Okay, and so this ellipse is the trickier one to draw because it's sort of on a weird slant to create that sort of perspective. So it's not going to look great, but hopefully that's not too bad. That gives you an idea of what it looks like. Imagine that like kind of flat on the XZ plane or XY plane. Let's take a look at our XZ plane here. So here's my X and Z axes. Now we're looking at an ellipse with x-intercepts at plus or minus 2, z-intercepts at plus or minus 4. So for z, let's go 1, 2, 3, 4, like that. 1, 2, 3, 4, like that. And so we're talking about an ellipse that looks kind of like this. Starts to look a little egg-shaped, right? And then finally, I want to look at my YZ plane. And again, my YZ plane is going to have y-intercepts at plus or minus 1, z-intercepts at plus or minus 4. So that's going to look like that. Kind of like that. Okay? And yeah, it's, again, my artistic skills are going to obscure what this is supposed to look like. So it's not the prettiest thing, but if I had software or something that I was using to create this surface, you would see that it's got kind of that shape that we refer to as an ellipsoid. You see that up here, which basically just means that all of its cross sections parallel to any of the coordinate axes always look like ellipses. Again, if I wanted to include more traces, for example, if I wanted to look at the traces in the in planes that are parallel to my xy plane, I might plug in z equals plus or minus 1. And that would give me another ellipse here and here. But again, if I start drawing that, it just makes this thing more messy looking. So that's an example of an ellipsoid. We'll do more in the next video.